Hello class, this is section 1.2 and in this video we are going to discuss the principle of conservation of energy. So remember, we are concerned about how energy flows inside an iron rod. So let's consider this rod and let's consider the segment of this rod between x equals a and x equals b. So let's think about how energy in that segment changes every second. So we're just considering that little region between A and B. We want to think about the rate of change of the energy inside that segment. So how does energy change? Well, the energy in that segment changes if you have heat flowing in or heat flowing out of that segment, and that's represented by the first bubble on the left hand side. Net energy flowing into segment every second. So net means you add the energy coming in and you subtract the energy coming out. So that's just the heat flowing. But you also have to consider the energy generated by the segment every second. So in the case where the rod is somehow generating heat, you have to consider how much heat is that rod generating every second. So this makes sense, right? I mean, the only way that the total energy can change is if energy flows in or out, or if the rod is generating energy. And remember, by the conservation of energy, energy never gets destroyed. It never just disappears. It has to flow out. One other thing we are assuming is that the cylindrical walls of the rod are perfectly insulated. So we can't have energy flowing outwards, upwards or downwards. It has to flow from left to right only. So we ignore the possibility that energy could leave any other way. Remember, in a previous video, we decided that the amount of energy between x equals a and x equals b is represented by integrating the energy density with boundaries a and b. We want to consider the rate of change of energy in the segment, so we have to include a t derivative here because a derivative in t represents a rate of change. So that's how to represent the left-hand side of this equation mathematically. As for the second bubble, the net energy flowing into the segment every second, what we have to do is that we have to add the energy coming in to the left and to the right. So remember that phi of AT tells us how much energy is the rate of energy flowing to the right at position A. So this tells us the energy that's coming in or leaving from the left boundary of the segment. We also have to consider the energy leaving or entering from the right boundary of the segment. And this is going to be minus phi bt. Now think a little bit about why we have a minus sign here instead of a plus. So remember, phi is positive if energy is flowing right, and phi is negative if energy is flowing left. So remember, if energy is flowing right from the x equals b boundary, it is leaving the segment. So we want to subtract in that case. If energy is flowing right from the A boundary, it is entering the segment, so we want to be positive in that case. And that is why phi of AT is positive and phi of BT is negative. In the same way, if energy is flowing left from the A boundary, phi AT is negative, and we want to be losing energy from the segment. And if energy is flowing left from the B boundary, then it's entering the segment, so we want that to be positive. So that's why the signs are what they are. If you don't understand that point, please take a moment, pause the video, and think about it a little bit. Lastly, we want to consider energy generated by the segment every second. But in the previous video, we already decided that this was another definite integral, this time of the internal energy, Q, xt, an x integral with boundaries a and b. But by using the fundamental theorem of calculus, we can simplify the second term. Remember that the FTC the fundamental theorem of calculus says that if you perform a definite integral on a derivative, you just have to evaluate the function at its bounds. So these two terms are equal by the FTC. Now please note that the bounds are from a to b, not from b to a, as are the other integrals here, because our a term is positive and our b term is negative. So we would like to switch the order of the boundaries to make it consistent with the other terms. Remember that we can switch the boundaries just by putting a minus sign in front. So we can make this minus an integral and have the boundaries go from x equals a to x equals b, like so. In fact, let us just collect everything on the right hand side under one integral. ba minus derivative phi xt plus qxt dx. So to proceed, we have to use this fact. If you have two functions and their definite integrals are always the same for every choice of boundary condition, then the two functions must in fact be exactly the same. Now this seems like something that makes sense. However, it is not that easy to prove. In fact, this was a homework problem I had to work on in my first year of math grad school. So this is not even an undergraduate level problem for most schools. However, it is true, and you are not really at the level where I think it's useful to demonstrate the proof, so just take my word for it. I do want to emphasize, though, that this fact is only true if all the definite integrals are equal. So let's say that the integral between 0 and 1 of two functions is the same. It does not necessarily mean that the two functions are equal. And actually, one thing that I forgot to do is that we have to switch the order of the integral and the derivative. Again, this is something that you can do, but I'm not going to explain why. You learn why you can do this in a class called Real Analysis, which is a class that math majors typically take in their senior year. But under certain conditions, you can switch the integral and derivative, and we are going to do that here. So when we use our fact and we get rid of all the integrals from a to b, we obtain the derivative of t with respect to t of e is equal to minus the derivative with respect to x of phi plus q. This is called the conservation of energy equation. And if you may forgive me for being a little bit sloppy in this video, we're not really working with the derivatives, we're working with the partial derivatives with respect to t and the partial derivatives with respect to x. And in fact, every single derivative in this video should have been a partial derivative rather than a regular derivative. However, I'm way too lazy to change this entire video, but in your homework, please remember to put in the partial derivatives. Even though I made the same mistake, I will penalize you for it if you use a d derivative. Alright, and this is the equation we get, and in the next videos we'll talk about how this leads to the heat equation.